So fourth lecture for Riccardo Penco, Effective Field Theories for Particle Physics and Beyond. So please, Riccardo.
Very good, thank you. Thank you, Enrico. So today we're going to continue with our discussion of chiral perturbation theory. So let me start by sharing my screen. Okay, can everyone see this?
Yes, I think so.
Perfect, great. So just as a brief reminder, let me start with a little recap. Yesterday we derived the chiral perturbation theory Lagrangian, which is a Lagrangian of an effective theory that describes light mesons. So mesons that are can be thought of as made of the U, D, and S quarks. And the first line here, I'm showing the leading term in a derivative expansion, and this first line contains all terms that are invariant under chiral symmetry, whereas in the second and third line I've added here the leading terms that explicitly break chiral symmetry. The second line contains the symmetry breaking effects due to the fact that the quarks are not exactly massless. Chiral symmetry emerges only in the massless limit. So when we take into account the fact that the quarks do have a mass, it is explicitly broken, but it is broken by a small amount. Similarly, chiral symmetry is also explicitly broken by electromagnetic interactions. And this is what this third line describes, again, a leading order in the symmetry breaking parameters that in this case is just the electric charge. Okay. And as I said, this theory describes 8 light mesons at energies smaller than 4 pi f, which is also our strong cupping scale lambda, which is of order of the GeV. Okay. Now, of course, we build this. So let's. So the first line we said is invariant under chiral symmetry, but more in general, the whole Lagrangian here is invariant. So the first line is also invariant under baryon symmetry in a trivial way, because the generator of baryon symmetry commutes with all the other spontaneously broken generators. So mesons are just neutral and they don't carry any baryon charge. But there is one more symmetry. Namely, this Lagrangian is invariant under a replacement of U dagger with U and vice versa. Which, if you remember our definition of U as an exponential of e to the 2i pi q, this symmetry is just at the level of the pi's equivalent to sending pi into minus pi. And this symmetry is responsible for the fact that in the action that I wrote above, only even terms appear. There are only quadratic, quartic, sextic, and so on terms in the Goldstones when we expand in powers of pi. Now, this is a discrete symmetry which doesn't have any counterpart in QCD. Okay, and in fact, it turns out that this symmetry doesn't appear to be respected by nature. Okay, where there are processes which we can observe, perhaps indirectly, of this form that sends, say, 2 mesons into 3 mesons, right? And therefore seems to imply the existence of interactions that involve odd numbers of fields. Now, how can we explain a process such as this one? Well, this process follows on the fact that we actually forgot one term in the effective action. And let's focus on the part of the action that is exactly invariant. Okay. All the terms in the first line are not just invariant under chiral symmetry, but they're actually, the operators in the Lagrangian are exactly invariant. Okay, they're exactly invariant as opposed to invariant up to a total derivative. Now, operators in the Lagrangian that are invariant up to a total derivative, provided the boundary terms can be neglected, still give a contribution to the action that is invariant under the symmetries, and therefore should be considered and should be included in the action. Okay? In the case of theories of Goldstone bosons, these terms are known as West, Zumino, let me write it down, West, Zumino, Witten, or WZW terms. Okay, and so this is what I'm gonna start by talking about today. Already, we saw last time that to write down exactly invariant operators, we needed to be a bit clever, right? And work in terms of this quantity U as opposed to directly in terms of the Goldstone fields. Because the Goldstone fields, we said, transform in a very complicated nonlinear way. In order to talk about and include West-Zumino-Witten terms, we'll have to be even more clever, okay? And so I will show you how this is done in chiral perturbation theory. A similar method can actually be followed in any theory of Nambu-Goldstone boson. Okay? This will look like a trick at first, but let's bear with me for a moment, okay? So the trick we're gonna use is extend for the moment our space-time from 4D to 5D in such a way that 4D space-time, the one that we're interested in, is the boundary of the 5D region. I'm not going to be too precise about how we're going to do that, but if you're interested in more details, you can look at the paper by Witten, I think 1989, that I'm citing in the notes. Okay. Now, in this 5D space, let's write down the following 5-dimensional action. And here I'm gonna write a coupling that depends on some arbitrary parameter lambda. And then I'm gonna add some extra factors just to make our life simpler later on. Now, in 5D, I can use an epsilon tensor that has 5 indices. And I'm gonna contract this with the following trace: U dagger dm u, U dagger dn u, U dagger dp u, U dagger dq u, and one more factor here. Okay. So you can convince yourself that using the transformation rules of U and U dagger under chiral symmetry, this quantity is manifestly invariant under chiral symmetry. Okay. However, if we expand this in powers of pi's, what you find is that order by order in pi, each term is just a total derivative. And therefore, it is essentially a boundary term, which means an integral over the 4D spacetime that we are actually interested in ultimately. So if I were to expand in powers of pi, a leading order, I would find that the first term would look like so: 64 lambda over 15 pi squared f to the fifth. And then we would have an epsilon mu nu lambda rho. Now, I'm going to write things in terms of the canonically normalized field, pi hat, just to remind you, they're related to the Goldstone fields, regular Goldstone fields, just by a factor of f. And so here we're going to have pi hat A, d mu pi hat B, d nu pi hat C, lambda pi hat D, d rho pi hat E, times the trace of a product of 5 SU3 generators. Okay. This is just a leading term. Then we're also going to have terms with higher powers of pi. Okay. So when you expand in pi, you see that each term can actually be expressed simply as an integral over ordinary spacetime. And notice in particular that this leading term that I wrote here is precisely a term that contains 5 pi fields, okay? And therefore, it's capable of explaining the decay process, or better, yeah, the scattering process that that I mentioned at the beginning. Okay. So I said at the beginning that Westermino-Witten terms have the property that are not exactly invariant, but they are invariant up to a total derivative. And it is easy to check this order by order in pi. In particular, since we kept only the leading order term in an expansion in power of pi, we're going to do the same when it comes to the transformation properties of pi hat. And at lowest order, as we mentioned also during the Q&A sessions today, the Goldstones simply shift under current symmetry. And you can check that under these shifts, this leading term here is invariant after the derivative. Because clearly when the Goldstones with a derivative acting on them shift, the shift, since it's a constant, just drops out. When this first guy shifts, what you're left with is something that you can rewrite as a total derivative by extracting one derivative, okay? And you should spend just a few moments after the lecture to convince yourself that that's indeed the case. Okay? So in chiral perturbation theory, it turns out that this is the only Westermino-Witten term that we need to consider. In general, for an arbitrary symmetry breaking pattern where some symmetry group G is broken down to a subgroup H, there can be more than one Westermino-Witten term. And in fact, their number is determined by cohomology. Okay, so there is an interesting connection with some fairly advanced notion in mathematics. I'm not going to go into it in details because it would take us too far away from the main discussion. But I added some references in the in my lecture notes if you're interested in exploring more this connection. So let me stop here for now and ask if there are questions so far.
So not for the moment, Riccardo. I don't see anything.
Okay, perfect. Then let me keep going. So there are, besides the fact that, as I just mentioned, Wess-Zumino-Witten terms are needed to account for phenomena we observe in actual experiments. There are some interesting formal aspects about Wess-Zumino-Witten terms. So let me start mentioning one, namely non-renormalization properties. And let's first talk about Carré perturbation theory, and then we can draw more general conclusion about Wess-Zumino-Witten terms. So for the particular term that I've written, it turns out that exactly invariant operators, and by that I mean every other operator that enters this first line here, cannot renormalize the coefficient in the Wess-Zumino-Witten term. Right? There is actually a simple way of seeing that, which is that, as I said, each exactly invariant operator is invariant under a discrete symmetry when we send the pi's to minus themselves, and loop corrections should preserve this symmetry, and therefore cannot generate a term that would not preserve it. This is a quick argument. In fact, it turns out that that this term doesn't get renormalized at all. Okay. Right. So not even by building loops out of the Wess-Zumino-Witten term itself. And that because topological considerations, which you can find again in the Witten paper that I cited before, tells us that the coefficient lambda that I wrote before, that is in front of the Wess-Zumino-Witten term, must actually be an integer value, an integer number. Okay. And as such, it cannot receive loop corrections that that would be fractional or real. So this is true for the Wess-Zumino-Witten term I wrote down. Now, how much of this is actually a general property of this type of terms? Well, number one, the fact that exactly invariant operators cannot renormalize with Wess-Zumino-Witten terms, that's actually a general feature. And to see that, we can use a fairly slick argument. And we can take the coefficients, the Wilson coefficients in the exactly invariant part of the action and promote them to spurions. Okay? So give them some space-time dependence, turn them into functions. Okay? If you perform this operation, all the exactly invariant part of the Lagrangian is still going to remain invariant. Okay? Performing this operation is not going to break any symmetry. However, if these terms were to renormalize the coefficient of a Wess-Zumino term, they would effectively also endow this coefficient with some space-time dependence. And now, if the coefficient in front here becomes a function rather than being just a constant, you can convince yourself that invariance up to a total derivative becomes goes away. Okay, it is no longer true simply because simply because if the change in the action was of the form lambda times some d mu o mu for o mu some quantity, then if lambda is a constant, this is a total derivative, but if lambda is a function of x, this is no longer a total derivative and the action is no longer invariant. Okay? And so this tells you that that such loop corrections would break chiral symmetry and therefore should not be, therefore cannot happen. Okay? So this is an argument that you can apply in general to any Wess-Zumino-Witten terms. The second property instead, namely the fact that the coefficient in front of Wess-Zumino term is quantized, that's actually a property of this particular Wess-Zumino term, and that doesn't always have to be the case. So for instance, there are interesting effective theories that people have considered. One that comes to mind are these Galilean theories that have found many applications in the context of cosmology as possible modifications of gravity. And the leading interactions in Galilean theories are in a derivative expansion, are terms that are invariant only up to a total derivative. Nevertheless, there is no topological argument that forces the Wilson coefficients in front of these Galilean interactions to be quantized. That's a counterexample. So two in general, it is not true.
Riccardo, excuse me. Let me interrupt you because there is a question which I think is pretty urgent from Sudipta. Can you explain again the advantage of going to 5D from 4D?
Yes. Actually, you've been very kind, Sudipta, because I think I actually haven't quite explained what the advantage is. So it wouldn't be again. So let me thank you for bringing it up. I should emphasize that. So you see, when we write when we start from a 5D action, this compact form is manifestly invariant under chiral symmetry. Okay? You can just see it by eye because we know how the U transforms under chiral symmetry. However, when we expand this in power of pi, and we use the fact that each term is a total derivative and rewrite it as an integral over d4x, then this whole infinite tower of terms, when put together, is not obviously invariant under the symmetries. So if we had to guess this by hand, it would have been a real pain to figure out how, what is the relative tuning between the quinti, the term with 7 pi's, and so on and so forth. It would have been very, very difficult to do. Okay. Parenthesis, historically, this is how people built these terms at first. Okay, this is how Wess and Zumino did it. It was Witten's insight that showed that what Wess and Zumino found could actually be written in a much more compact way, and that in fact the coupling in front should be quantized for topological reasons. So this idea of writing terms in 5D that are total derivatives is the standard strategy for building Wess-Zumino-Witten terms, because when you write them in 5D, you are sure that they are going to be invariant. And then when you put it down to 4D, you can expand things and knowing that by construction, all these operators that you're adding up must give you something that is invariant. So I hope that answers your question, Sudipta. If not, feel free to follow up.
Yes, so there is no follow-up for the moment. I will let you know. Okay,
great. Thank you. Now, another interesting aspect about Wess-Zumino-Witten terms is that they have a connection with anomalies. And from our viewpoint, this is nice because it will. So we've seen how spontaneously broken and approximate symmetries are implemented in effective theories. Now this will give us a chance to discuss a little bit how anomalous symmetries can be implemented. Okay. So this Wess-Zumino-Witten term that I wrote at this point doesn't involve couplings with the photon, with electromagnetism. Okay. So let me now add that. Let me include the photon. It turns out that because this term is invariant up to a total derivative, obtaining a term that is gauge invariant is not as easy as replacing ordinary derivatives with covariant derivatives. Okay, it's actually more tricky. And let me copy here. Here, there we go. Let me copy this because otherwise I'm going to spend an inordinate amount of time just typing this back up. This to give you a sense, this is the term that you will need to add to what I wrote before in order to obtain an action, a term that is actually gauge invariant. Okay, and you see the tricky aspect is that the part that is the form that is manifestly invariant involves derivatives with respect to the 5D coordinates. However, our gauge field only has 4 components. And so that's why you cannot just promote regular derivatives to covariant derivatives, and you need to be a bit more clever. Okay? But you know, with a little trial and error, this is exactly the result that you obtain. And now, if you expand in powers of the canonically normalized fields, again, this correction, what you find is that these terms, among many other terms, contains also something of this form. Lambda e squared, 48 pi squared over f, pi hat 0, epsilon mu nu lambda rho, f mu nu f lambda rho. Okay. So this is a trilinear interaction that involves 2 photon fields and the pi 0 field. And this interaction can be used to describe the decay process of a pi 0 into 2 photons. And as some of you may know, this result is due to the fact that the symmetry associated with pi 0, so the one generated by the SU3 generator associated with pi 0, is anomalous. Okay? So let me call this generator Q3. Okay? That's how conventionally it is denoted in the literature. So it's, you know, on my SU3 generator, if you remember, I denoted them with QA, and now I'm looking at the one with A = 3. As you said, this is anomalous. And so to that means that quantum effects are breaking this symmetry, and in particular that there is no conserved quantity associated with this symmetry. So to see that, we can follow the standard Noether argument to derive the Noether current associated with the symmetry Q3. Okay, and just to remind you, a quick way of calculating the Noether current usually is to perform the symmetry transformation that you're interested in with a parameter that is local, so that depends on space-time rather than being a constant. Right? So if the parameter was a constant, the action shouldn't change by definition of symmetry. When you consider a parameter that depends on space-time, in general, the change in the Lagrangian is going to have this form if alpha is such parameter. And the J mu in front is precisely the Noether current. And so if you integrate by parts, this tells you that the coefficient in front of your transformation parameter is precisely the statement of the conservation of current. Okay, very good. So if you play this game with our Weston-Witten Lagrangian and with chiral perturbation theory, we find that d mu J mu 3, you don't get just d mu J mu 3, but what you get is an equation of this form, right? So normally you would have, if this was really a symmetry, you would have d mu J mu 3 equals 0. Right? Instead, now the for divergence of the current associated with Q3 doesn't vanish, but it's proportional to this factor. Okay. So the fact that the for current doesn't vanish is the statement that your symmetry is anomalous. And as you mentioned a few times during the Q&A, this factor here is an exact result, okay? So it is valid at all order in loops. And it is an operator statement between that relates the divergence of the current operator with this particular combination of the field strength of electromagnetism. So because it is an operator statement, it should be valid in general, not just in our effective theory, but also in QCD. Right? And in fact, we can rederive this result with a one-loop calculation in QCD. And by doing that, we can actually figure out exactly what this coupling lambda should be. So far, I only told you that lambda should be an integer. But the calculation in QCD allows us to figure out what lambda should be. And it turns out to be equal just to the number of colors in QCD. So you can calculate that theoretically, but of course, you can also verify that experimentally. Because you see, if you look at this coupling here, it depends on lambda and on f. Okay? But if you measure f by some other process, for instance, by looking at the leptonic decays of the pi, then once f is nailed, you can use you can calculate the decay rate of the pions and compare it with observation to figure out what lambda should be, and you find that lambda indeed must be 3. Okay. So, okay, let's see, let me ask if there are more questions.
So not for the moment, Riccardo.
Okay, so then maybe I'll continue, and Enrico, you just jump in if there are pressing or even non-pressing questions.
Absolutely.
Okay, thank you. So, okay, let me also make one comment to draw a distinction between anomalous symmetries and explicitly broken symmetries. Okay? So after all, you could think, okay, in both cases, at the end of the day, the symmetry is not there. So is there really a difference between these two situations? And you see, as I said, this relation for divergence of the current is an exact result. Okay, so the right-hand side, that's it. There are no further corrections to that. That's the only term that spoils the conservation of the current. Instead, if you have explicit symmetry breaking terms in your action, then typically each of these terms will contribute to the right-hand side of the conservation current conservation equation, and will prevent you from having a conserved quantity. Right? So from this viewpoint, compared to explicitly broken symmetries, anomalous symmetries are conceptually distinct. Okay, are very special, because we can calculate exactly what the right-hand side should be, and there is only one term that appears. Okay, so that's the first comment I wanted to make. The second one goes back to another a point at the beginning of last lecture, where we invoked anomalies for a different reason. So if you remember, when we neglected electromagnetic interactions and quark masses, we said that the QCD Lagrangian, including only the light quarks, was invariant under 2U3 symmetry, which we proceeded to break down to the following factors. So the chiral factor, then we had the baryon symmetry, and then we had an axial symmetry. And what I said back then was that we didn't need to worry about the axial symmetry, because the axial symmetry was anomalous. Okay? And so it wasn't really a symmetry of the theory, and therefore we don't need to worry about it. And instead we focused on chiral symmetry, which, as you may remember, was spontaneously broken by the VEV of the following operator. Okay. Now notice that if U1A had not been anomalous, it would have been spontaneously broken by this very VEV. And therefore, we would have had one more Goldstone. We would have had 9 Goldstone modes rather than just 8. However, because it's anomalous, we just discarded it, and we didn't consider this 9th Goldstone. So now, some of you might wonder, why didn't we do the same with the pi 0? So I just told you that the symmetry associated with the pi 0 is also anomalous. So why did I consider it, whereas I did not consider the axial symmetry? Okay, and the difference between these two symmetries lies in the reason why the axial symmetry, the axial current is not conserved. So you can derive a very similar result to the one for the conservation of current for Q3 in the case of the axial symmetry. And what you find now is that, as expected, the axial current is not conserved. But the non-conservation now is due not to the electromagnetic field strength, but is due to the field strength of QCD. So exactly as the previous equation for the conservation of current, this equation as well is an operator statement, which therefore should be valid at all energies, okay, both in our EFT and in QCD. Now, in QCD, we have a very well notion of what the gluon is, and therefore its field strength. But at scales below confinement, there is no longer trace of any gluons. Okay. So the right-hand side of this equation becomes trivial, and the only way of satisfying it also within the EFT is for the left-hand side to be trivial as well, which means is to not have any axial symmetry, any remnant of axial symmetry at low energies in the EFT. And that's why we were able to, and it was the correct thing to do, to completely forget about the axial symmetry and not consider the Goldstone associated with it, but instead consider the Goldstone associated with Q3 and therefore the neutral pion.
So Riccardo, let me jump in quickly.
Yes.
So there is a question from Lucas who is asking, could you explain again why this result, I guess the anomaly, should also be present not only in chiral perturbation theory but also in QCD?
Yes, it's because
actually, he's satisfied. Yeah. He just wrote me that you just answered his question during the lecture.
Okay.
Okay. So I think it's all right. Good. We have another question from Jonathan, which I'm not sure I completely understand. Maybe you understand it, which is asking: is CPT symmetry related to mass conservation?
So. I'm not sure I understand the question either, to be honest.
So, Jonathan, what do you mean with mass conservation? What do you mean in this case? Maybe we can move on, waiting for Jonathan to qualify better the question. No, sorry. There is one more question from Sanket.
Okay.
Who is asking if you can explain again the difference between Q3 being anomalous and U1A being anomalous.
Yes. So I think that so both these symmetries are anomalous because when you derive an equation for the conservation of for current, the right-hand side doesn't vanish, but it's proportional to some field strength, okay, some contraction of field strength. The difference lies in the fact that for Q3, what gives you the anomaly is the electromagnetic field strength. Okay. And the photon is a field that belongs also in your low energy FT, in chiral perturbation theory. And therefore, you can realize non-trivially this operator statement in chiral perturbation theory. The right-hand side is non-zero because you have a photon around, which means that you are allowed to have some notion of symmetry associated with Q3, and therefore an associated Goldstone mode. Instead, for axial symmetry, the non-conservation of current is due to the gluon field. And when you go at scales below confinement, there is no trace of gluons anymore. The right-hand side becomes trivial, and therefore the left-hand side of this equation must be trivial as well, which means there shouldn't be any remnant of axial symmetry at low energies. So I hope that that answers the question. If not,
okay. If not, Sanket, let us know.
Yeah.
Okay. So for the moment, it's okay. There are no further questions. Okay, and Sanket is satisfied.
Great.
Okay.
Excellent.
Good.
Okay, very good. So now, since we are discussing anomalies, I'm sure that Andrea talked a lot about them in his lectures, so I won't go too much in depth. But I just couldn't resist the temptation of saying something about gauge anomalies. And well, some of you that attended the Q&A, we've also had a discussion about gauge anomaly, I think, during the first Q&A. So the standard law, as you may know, is that anomalies of global symmetries usually are perfectly fine, and in fact, they have phenomenological implications. So for instance, they give you the right decay rate for the pi0 into 2 photons, or they prevent the existence of a 9th light meson. And these are all things that can be verified in experiments, right? And in fact are. Gauge anomalies instead have a very bad rep. So usually are thought to, people think that the standard law is that gauge anomalies should be avoided at all costs, because otherwise your theory is going to be inconsistent, okay? And so what I'm going to argue here is that in the context of, if you view your theory as an effective theory, we can actually be a little more laissez-faire with respect to gauge anomalies. And it is permissible to have a fermion content that such that the anomaly doesn't cancel, but the price to pay is that your gauge field must have a mass. Okay. So let me just show you this in a specific example. Okay. And by the way, if you want to read more about this, there is a beautiful paper by John Preskill that discusses precisely this issue, the issue of gauge anomalies in effective field theories, and you can find it cited in my notes. And I really encourage you to take a look at it. It's a beautiful paper. So, in fact, the example that that I'm going to give you is essentially lifted from his paper. So, let me consider a U1 gauge field coupled to n left-handed fermions. So I'm going to write their kinetic terms. So these are Weil spinors. And therefore, rather than having the usual gamma mu matrix, I have here this sigma bar mu matrix. And for those of you that are not familiar with Weil spinors necessarily, so this sigma bar mu matrix is simply a collection of 4 2x2 matrices, the first one being the unit matrix, and the last 3 being minus the Pauli matrices. Okay. So you can check with a one loop calculation that the U1 symmetry, the U1 gauge symmetry of this theory is anomalous unless the following condition is satisfied. Okay. So in order not to have an anomaly, this quantity A, sometimes also referred to as the anomaly coefficient, which is just the sum of all the charges cubed, must vanish. Okay. And so the standard law would be that if you want to work with such a theory, you need to make sure that you choose the charges in such a way that this combination vanishes. So now let me modify this theory a little bit and add the following pieces to it. So I'm going to add first a complex scalar which is charged under the U1 and has a Mexican half potential, so that the scalar will acquire a VEV V. And then I'm going to couple the scalar with the Yukawa coupling just to the end spinor. So invariance of this Yukawa coupling under the U1 implies that the end charge should be equal to 1/2, because here I just chose the charge of phi to be equal to 1. And therefore, the first comment I can make is that having a coupling only between the nth fermion and the scalar, it's a technically natural thing to do, provided Qj for j different from n is not equal to 1/2. In which case, this is really the only thing that you could write down that preserves gauge invariance. Okay. Very good. So my assumption is going to be that when I sum over all n of these fermions, that the anomaly coefficient does indeed vanish. Okay, so that this theory does make sense according to the standard law, and so there is no anomaly in this fundamental theory. Now, if I expand phi around its VEV, so as usual, v plus sigma e to the I pi, and say I work in unitary gauge where I set the pi to 0. What I find, of course, is that by Higgs mechanism, some of my particles acquire mass. And in particular, the gauge field acquires a mass 2 eV. Well, I should call it the sigma, I guess. The sigma gets a mass which is square root of 2 lambda times v. And the nth quark acquires a mass due to the Yukawa coupling, which is 2 IV. And I should say that I might be working in units such that 2 is equal to square root of 2 is equal to 1, meaning that the factor of 2 might not be exactly correct, but then they won't play any role. Okay. So let's now consider the region of parameter space where the Yukawa coupling is of order square root of lambda, but both of them are much larger than the electromagnetic coupling. So as a result, this means that Mn and M sigma are much larger than the mass of the gauge field, and therefore can be integrated out. And of course, all other fermions just remain massless. So when we integrate out the fermion, the nth fermion, and the scalar, we're left with a low energy effective theory that only involves the massive gauge field and the massless fermions. And in this effective theory, since we're left with only n-1 fields, by definition, since the anomaly coefficient was 0 in the full theory, this is also equal to Qn minus Qn cubed, which is minus 1/8, which is different from 0. Okay. So if you were to look at this effective theory by itself, you perhaps would be troubled by the fact that the anomaly doesn't seem to cancel. And yet we know that this effective theory admits a UV completion that is perfectly sensible, meaning one in which the anomaly cancels out. Of course, so in this example, you see that I had to arrange things in such a way that the gauge field was massive. And in fact, this is a general result. Okay, we are allowed to work with effective theories such that have a fermion content such that the anomaly doesn't cancel. But the price to pay is that to be consistent, your gauge field also needs to be massive. Okay, and it makes sense given that what protects the mass of the gauge field, if you want, what set it to 0, is the gauge symmetry itself. And if the gauge symmetry is anomalous, then it is natural to have a mass if the gauge symmetry is not there. So we can also derive a lower bound on the mass of the gauge field using some naturalness arguments. Okay. So imagine that you start with MA equals 0 in the full theory. And that you try to perform a matching between the full theory and the low energy effective theory. And you do it as we did it for the toy model. So by comparing diagrams loop by loop. Okay. So at 3 loop, there exists a diagram of this form. Where the solid lines denote the nth fermion, the one that let's say has a mass and therefore a heavy mass and therefore which we will integrate out. So it turns out that to match this diagram in the effective theory, we need to include a mass term for the photon, which has essentially the following value schematically. There is this is a 3-loop diagram, so we have 3 loop factors, 1/4 pi squared. We have 6 vertices, each proportional to the charge of the nth quark. And then, since we said we started with by setting the mass of the gauge field to 0, the only scale in this diagram is the mass of the nth fermion. And in dimensional regularization, there is no other scale that can appear. And therefore, by just dimensional analysis, this should be proportional to the mass, to the nth mass, let's say. Okay, so very good. I can actually shuffle some of these factors around, and I can rewrite this result in the following way: E/4 pi to the 6th. Now, using this result, I can trade the Qn for a sum over all other charges cubed. Everything squared. Times essentially what would be the strong cupping scale of my effective theory if I integrated out the nth fermion, the heavy fermion. Okay. And the reason why this expression is nice is because it contains only factors that make sense in the context of the low energy effective theory. Right? Contains the electromagnetic coupling, which is something that one could measure at low energies. It contains the anomaly coefficient, which is something that one could calculate by looking at the fermion content at low energies. And it contains the strong coupling scale, of the EFT. Right? So in fact, this result is would be also fairly easy to guess, okay? Because you see, if you look at this Lagrangian, the only combination that makes physical sense is E times Qj. Okay? I can only rescale E by a factor and Qj by the inverse factor, and the Lagrangian remains invariant. So that's the only physical combination that can appear. Is EQJ. And so that's one consideration. The second consideration is that it makes sense for this mass to depend somehow on the anomaly, be proportional to the anomaly coefficient, which is, if you want, the quantity that that breaks the U1 symmetry. And the sign of E is also not physical. So the mass should depend always on even powers of E, which forces, together with this condition that E and Qj should appear together, it forces this result to be proportional to the square of the anomaly coefficient rather than the anomaly coefficient itself. Right? And finally, the strong coupling scale is the only scale you have around if everything else is massless, and therefore that's what should set the mass of the gauge field. Okay. So very good. So this was just to yeah, this is all I wanted to say about gauge anomalies.
Sorry,
if you look at the paper, yeah.
Sorry, let me jump in because we have a very quick question.
Sure.
Sudipta is asking, why does the anomaly have the form of sum of cube to the cube?
Okay. Essentially, it has to do with the fact that when you look at the, when I always say you that you can show that the current is not conserved by calculating a one-loop diagram. The one-loop diagram that I have in mind is something that might be familiar to those that have learned anomalies. Is a triangle diagram of this form, where the fermions are running inside the loop, okay? And so now these three vertices are proportional to the charge of each fermion. And you need to sum all possible diagrams where you have the first fermion running the loop, the second, the third one, the fourth one, and so on. Okay? And so when you sum over all of them, your final result, which tells you whether the current is conserved or not, is going to be proportional to the sum over all the quarks that can run in the loop of Qj cubed. So I hope this answered your question. And by the way, in light of this, you can also see that this three-loop diagram is essentially two copies of the typical triangle diagrams that people calculate to show that there is an anomaly, just glued together. So it's no surprise that it plays a role in showing that the gauge field must have a mass.
So we have another very quick question. Oppo is asking, is the triangle anomaly an example of gauge anomaly?
It depends. So it depends on whether the current that is, or the symmetry that is anomalous is a gauge symmetry or not. So in general, you always calculate for chiral anomalies, you always end up calculating these triangle diagrams, and whether or not the current that is anomalous is coupled to a gauge field determines whether what you're talking about is a gauge anomaly or not. I hope that answers the question.
Okay, Riccardo, there are no further questions for the moment. Yeah.
Okay. Very good. So then let's zoom back out for a moment. And now we're gonna switch gears and change topic a little bit. If you remember, I started our discussion on chiral perturbation theory saying that it was gonna allow us to discuss how sometimes it might not be easy to implement symmetries in effective theories, right? If you remember, writing all terms compatible with the symmetries is our second ingredient to build an effective theories. And I tried to argue, discussing chiral perturbation theory, that sometimes when symmetries are nonlinearly realized, or when they're approximate, or when they are anomalous, one needs to be a little careful, and there are subtleties that need to be considered. Okay. So now what we're going to do is change topic to actually discuss possible subtleties that can arise in implementing the third ingredient of effective field theories, namely having an explicit power counting. Okay, so being able to assign to each operator in the Lagrangian a specific order in our expansion parameter. And so the example that I would like to consider to discuss this is the example of non-relativistic theories, and in particular non-relativistic fermions. So until now, both the toy model that we considered and chiral perturbation theory, in its simplest formulation, was a theory where there was only one expansion parameter, namely a ratio of energy of the typical processes we were interested in over some strong coupling scale. Okay? This made the power counting particularly easy because each derivative in the Lagrangian simply scaled like a factor of the energy. All components scale the same way. Okay? Now, just for a few moments, I'm gonna reintroduce powers of C. Okay. Now, imagine that rather than considering relativistic particles, so either massless or particles with an energy much larger than their mass, as we did for our toy model, imagine that we're interested in scattering of non-relativistic particles, meaning particles which have a momentum with magnitude much smaller than mc. When that is the case, then let's say if these are fermions, derivatives acting on the fermion field now are going to scale schematically in the following way: minus mc mp. Okay, so a derivative with respect to time is going to pull down a factor of the energy, but because the particle is non-relativistic, the energy is going to be dominated by the rest mass of the particle. And therefore, this zero component is not going to scale with momentum at all. So this inhomogeneous scaling a priori is not necessarily a showstopper. It actually happens frequently in effective theories. The more problematic aspect is that we are saying that time derivatives now scale like a mass. They don't scale like momentum, which means that at very, very low momenta, derivatives are not necessarily more suppressed. So this should be contrasted with what happened with our relativistic theory, where at very, very, very small energies, derivatives became more and more and more suppressed. So whenever we are interested in a kinematic regime where the derivatives don't have a good scaling, there is always a basic trick that we can use. And we will see different ways of implementing this trick tomorrow. And we will start today. And this trick is simply a rephasing of the field. The particular example I'm considering here, what we're going to do is introduce a new field, is e to the minus mc squared t, different from psi, okay? Our new field is this psi tilde. Now, if you invert this relation for psi tilde, and you let a derivative act on psi tilde, you can convince yourself that I chose this phase precisely in such a way that when the derivative acts on the phase, it's going to cancel out the rest mass and give me a zero component of the derivative, which now scales up to a sign like the non-relativistic, and up to a factor of c, like the non-relativistic kinetic energy of a particle. So this solves our problem because now both the zero component of the derivatives and the spatial components become smaller as we go to small momenta. It just so happens that the energy vanishes faster with momentum than the spatial components do, but that's okay. So let's see how this can be implemented explicitly. Say if we start with a relativistic fermion, and let's do the matching to go from this relativistic theory to a theory that describes non-relativistic fermions. So the simple toy model I'll consider is just a standard kinetic term for a Dirac field. And I won't even introduce any scalar here. So rather than considering a quartic interaction with the gamma 5, let me just consider a regular quartic interaction. So what is convenient to do is, so what we can do now is rewrite this action in terms of psi tilde rather than psi, okay, by performing this replacement. And then it's convenient to break up psi tilde into two parts using a projector, psi tilde plus and psi tilde minus. This is not dissimilar from what we did in chiral perturbation theory when, better, in QCD, when we broke quarks into their left-handed and right-handed parts, except that now the projector we're using is defined using gamma 0 rather than using gamma 5. Right? So it turns out that we can integrate out psi tilde plus perturbatively in an expansion in powers of p momentum over mc, okay, or to the extent that the momentum of a non-relativistic particle is m times v. This can also be thought as an expansion in powers of velocity over c, which makes very much sense, since we want to take a non-relativistic limit. So because of this projection, both psi tilde plus and psi tilde minus have only two independent components. And if I denote psi tilde minus, which is the field that I want to keep, as 0 little psi, where this little psi is a 2-spinner now, the effective action that I obtain by integrating out psi tilde plus at lowest order looks like this. We have psi dagger I dt plus Laplacian square over 2m psi minus a quartic interaction now for this 2-spinner, which is inherited from the one for the Dirac spinor we had above, plus, of course, all sorts of non-renormalizable terms. Okay. So just as a simple exercise, let's now see how power counting works in this effective theory, this non-relativistic effective theory. So we saw before that a derivative with respect to time, when acting on the psi tilde and therefore on this 2-spinner, is going to scale like p squared over m, whereas a derivative with respect to spatial coordinates is going to scale like p. And so from this, I get that t should scale like p to the minus 2, x should scale like p to the minus 1, which means that the integration measure should scale like p to the minus 5. Right? So this is different from the scaling in energy for a relativistic theory, where the measure, if you remember, scale like to the minus 4. By demanding that the kinetic term is of order 1 in our expansion parameter, we can read off the fact that psi must scale like p to the 3/2. And therefore, we can automatically get the scaling of this leading interaction that I wrote down, the quartic interaction. This scales like p to the minus 5. This scales like p to the 6, which means that the whole interaction scales like p and goes to 0 at for 0 momentum, which is to say that this interaction is not normalizable or an irrelevant interaction. Okay. So for non-relativistic fermions, it is not possible to write down renormalizable or either relevant or marginal interactions in vacuum. And so this is probably not very surprising, because at the relativistic level, it's exactly the same, right? The theory we started with this quartic interaction, that was a non-renormalizable interaction to begin with. So it's not that the situation became any worse in this sense by taking the non-relativistic limit. However, something we'll see tomorrow is that, interestingly, the situation changes when you turn on a finite density of fermions. Right? So at finite density, the power counting rules change, and there exist interactions that are marginal, and in fact, when you include loop correction, marginally relevant. Okay, so before turning on a finite density, let me just spend the last 10 minutes discussing symmetries, the symmetries of this action that I just wrote down, okay? Because it will allow us to see a few more different instances of how symmetries, of the role that symmetries can play in effective theories. So is it okay, Enrico, if I just go ahead, and then if there are any questions, we just address them all at the end?
Absolutely, yeah.
Okay.
Feel free to continue.
Perfect. So this leads me to the discussion of contracted and accidental symmetries. Okay, so the notion of accidental symmetries is fairly standard. That of contracted, not so much. In fact, I might have even come up with the name myself, so it's non-standard at all. Nevertheless, it's an instance that, you know, it's something that can actually happen. So, let me tell you what that is about. So if we look at this action here, this effective action, it enjoys a variety of symmetries. Of course, because there is no explicit dependence on space and time anywhere. We have invariance under space-time translations. And we also have invariance under spatial rotations, right? So for instance, the spatial derivatives have indices that are contracted to form a Laplacian. Now, more interestingly, this action is invariant under Galilean boost, okay? Meaning transformations that do not change time, but as we know, send coordinates into coordinates minus b times t. This makes sense, of course, because we're taking a non-relativistic limit, and we know that well before discovering special relativity, physicists actually thought that this transformation described a change of frame, and the nature should be invariant under changes of frame, and therefore, as long as you went from an inertial to another inertial frame, and therefore it makes sense that the theory should be invariant under this symmetry. And the way in which this is enforced is by having this particular combination of derivatives. Okay, so this combination of derivatives is precisely what the right combination that is invariant under Lorentz boost. Under Galilean boost. Exactly in the same way that in a relativistic theory, it is the contraction d mu that is invariant under Lorentz boost. So what this simple example shows us is that when you go from some UV theory down to an EFT, symmetries can actually change. Symmetries can change, and in particular, I would call Galilean boost a contracted symmetry, because the algebra of Galilean transformations is a contraction, also known as Inonu-Wigner contraction. You can read more about it on Weinberg's field theory book. It's an Inonu-Wigner contraction of the Lorentz algebra. When you introduce factors of C in the algebra and you take the limit where C formally goes to infinity, you recover the Galilean algebra. Now, there is also one more symmetry that we should discuss, which is an internal symmetry corresponding to U2 unitary rotations of these two spinors. Okay. So something of the form psi I goes to Uij psi j. And it's convenient to break up this internal symmetry into two factors, one an SU2 and a U1 factor. The U1 factor here is just essentially inherited by the U1 symmetry of the relativistic action that we started with. The conserved quantity that corresponds to it is just the conservation of particle number. Now, in a relativistic context, the quantity that is conserved is the number of particles minus antiparticles. In the non-relativistic limit, where you don't have enough energies to produce particle-antiparticle pairs, It's the actual particle number that is conserved. Now the SU2 instead is a new, compared to the relativistic theory, an accidental symmetry. Okay, these are just spin rotations. So as you know from your quantum mechanics courses, spin is an internal symmetry in a non-relativistic context. In a more precise sense, from the viewpoint of a low energy EFT, which receives corrections suppressed by P over MC, this internal symmetry is just accidental, in the sense that there are higher order corrections suppressed by power of C, such as, for instance, spin orbit coupling terms, that will break spatial rotations and spin rotations explicitly down to the diagonal subgroup where these two rotations take place simultaneously. And that follows from the fact that spin, from a relativistic perspective, it's just that spin is just a finite dimensional representation of, if you want, the Lorentz group. Very good. So in light of all these symmetries, if you look back at our effective action for non-relativistic fermions, you find that you could have basically guessed this form purely starting from particle content and symmetries. There is only one exception, namely the fact that we could have also added a term of the form psi diagram psi, okay, something quadratic. And in fact, based on our power counting rules, this term would be relevant. And so you might be worried, given that it looks a bit like a mass term, you might be worried that perhaps there might be some naturalness problems lurking, okay? Even though we've seen that in a relativistic context for fermions, there are no such problems. But still, it's always better to be safe than sorry and check. And you can check that if you calculate a one-loop diagram, which you would expect to give a correction and generate a term of that form, you find that in the relativistic context, and so let me focus on zero external momentum, which is what would be relevant if we were looking for a renormalization to the mass term, quote unquote. You find that the loop has this form up to an I epsilon factor. And by rescaling E, by defining E prime equal to 2m E, you can pull out any scales from this integral. And now this integral becomes scale free. It is a UV divergence integral, but we know that in dimensional regularizations, UV divergence integrals that don't contain any scale just vanish. And so this shows you that it is, at least at one loop level, it is consistent to set to zero this term because a one loop correction is not going to generate it for you. And as we will see tomorrow, it makes also sense from a physical viewpoint, the fact that this term can be set to zero. And that's because adding it to the Lagrangian would correspond to adding a non-trivial chemical potential to your theory, which is this mu nr, would mean turning on a chemical potential and therefore putting your theory at finite density. Okay? So that's something that an experimentalist can choose to do, and therefore it makes sense that quantum corrections are going to leave an experimentalist the freedom of adjusting these coefficients any way they may want. Okay, but we'll discuss fermion theories of non-relativistic fermions at finite density tomorrow. For now, let me stop here and see if there are any last questions.
Yes, Riccardo, thanks a lot. So we have a few questions. So we have a couple of questions about gravitational anomalies.
Okay.
So let me go through them. So the first one is from Sudipta, who is asking, should we worry about gravitational anomalies for any energy scale?
Yes, I would say, sorry, let me qualify this for a moment. So the graviton is massless, exactly like the photon was in the case of the anomaly for the Q3 symmetry. So this tells you that at any it tells you that at any scales you are going to have to satisfy a non-trivial operator equations for the conservation of current. Okay. And so now, then, other than that, I hope I convinced you that anomalies are not something that you should be worrying about, in the sense that if there are global symmetries that are anomalous, then it's fine. You're going to have some signatures, and if it is gauge symmetries that are anomalous, then you are within an effective theory. Then it just means that your gauge boson is going to have mass.
Okay, so we have another question from Tessio, always about gravitational anomalies. So Tessio is asking, what kind of bad behavior, is any, can we expect to see in a gauge theory in which the gravitational anomaly does not cancel?
So, by the way, I'm assuming by gravitational anomaly that you mean so mixed anomalies, meaning situations where the forward divergence of the current of some internal symmetry is proportional to the square of the Riemann tensor. Okay. So
yes,
I'm not.
Yes.
Yeah. Okay. So I'm not an expert of that, to be honest. Maybe that's something we can bring up also tomorrow at the Q&A. At the Q&A sessions. I don't know if Enrico, you know of any deep methodologies.
I would suspect that the gauge boson acquires a mass.
If it's a gauge anomaly, yeah.
If it's a gauge anomaly, yes, because of the same argument that you gave in this lecture.
Exactly.
If it's global, okay, I think as usual there are no problems.
Yeah, and I think again, even in the gauge theory, the problem comes about if what you're trying to describe is a phenomenon in nature that involves some long-range forces mediated by a gauge boson that has to be massless, like in the case of electromagnetism, right? So then it better be the case that the symmetry associated with gauge boson is not anomalous. But usually that's going to be, I think, nature is going to tell you if you are allowed to have these anomalies or not.
Yeah. So Tessio, if this is not satisfactory, please bring up the question again tomorrow in the Q&A session, that we can discuss it again. Then we have one last quick question from Lucas, who is asking, can you quickly go over again on why there is no Navier-Stokes boson due to the U1 axial?
Okay, yeah, sure. So maybe I was a little too quick in stop the sharing. So let me go back to where are we? Here, yeah, this page. So the fundamental difference is the gauge field that causes the symmetry generated by Q3 and the axial symmetry to be anomalous. Okay. In the case of the axial symmetry, you see that the non-conservation of current comes about because of the field strength of gluons. Now, I try to emphasize that this relation for the current is an operator statement. So it's something that should be valid at all scales in principle. However, at low enough scales, below confinement, you don't have any trace anymore of gluons in your theory, right? When we wrote chiral perturbation theory, we focused on the mesons and there was no remaining strong force around. And so this means that the only way to satisfy this operator statement at low energies is to satisfy it in a very trivial way, where on the right-hand side, there is no gluon field in your theory, and on the left-hand side, there is no axial symmetry in your theory. Okay? And that's the reason why we didn't include axial symmetry to begin with when trying to build a chiral perturbation theory.
Okay. So we have another quick question, always about anomalies.
Okay.
So, okay, if you don't mind, Riccardo, let me ask you this one, then we are going to close because it's going to start to be a bit late.
Sure.
So why only so Sudipta is asking, why only triangular diagram is important for anomaly calculation? Is there any higher order diagram?
Yes, very good. So the answer is no, there are no other higher order diagrams. And from a perturbative calculation, that might seem a bit surprising, although it's something that can be proven. And by the way, I'm referencing some TASI lecture notes on anomalies and in my lecture notes. So they are very, very nice. So in there, you find an explicit discussion of why anomalies are one loop exact, meaning that a one loop calculation is enough to derive this result for non-conservation of current. Okay. But I think also another viewpoint on that is you can derive this result also by the way Fujikawa did it, meaning showing that the currents are not conserved when you have an anomalies because the measure in the path integral, the fermionic measure, is not invariant. Okay? And so if you calculate how the determinant, how the measure changes under a chiral transformation or an anomalous transformation in general, you find that it changes precisely by the amount due to the anomaly. I think in that language, probably it's more clear that this result is not coming from, it's not just a first order result in a loop expansion.
Okay, so if you guys have further questions about anomalies, please bring them up tomorrow in the Q&A session that we will discuss again. Okay, so I think this is a good moment to stop. We're already 10 minutes after the time. So Riccardo, once more, thank you very much for the very nice lectures. I would also like to thank everybody for the participation, for the very stimulating questions. So we reconvene tomorrow morning. Tomorrow morning again, first lecture will be Standard Model by Andrea Romanino, and the second one, Cosmology by Rogerio Rosenfeld, and then so tomorrow we finish the first week of the school. So half is almost done. Okay, so thank you very much.